All right. Hi, everyone. So today, in today's discussion, we're going to be talking about dynamic programming and complexity theory. So maybe you've heard of some of these topics before, maybe you haven't, and that's okay. So we're going to go over them. All right. So dynamic programming. So for dynamic programming, we're going to go over a Fibonacci examples. We're kind of going to get a sense of like what dynamic programming is. And then we're going to talk about some properties of dynamic programming and approaches you can take for it. And then we'll go over different examples as well. Then we're going to go over complexity theory. So we're going to go over P and P and complete and some examples on those. If you've heard of those before, great. If you haven't, that's okay too. I think they're really cool and one of my favorite parts of this course. So I hope you get something out of it. It's just maybe not something you'd be applying every day. Depends what you do within computer science, but it's still very interesting stuff and it's good to know and have an understanding of for sure. So we'll talk about that. But dynamic programming, that's a lot more applicable to maybe even everyday kind of stuff. So we'll jump into it. So we're going to talk about the Fibonacci example first. So maybe you can kind of think about how to write Fibonacci recursively, right? And here we actually see it written recursively on the left here, right? So the way we do that, right? And just to remind you, Fibonacci numbers are like this. So it's like 1, 1, 2, and then 3 and 5. And what we're doing is we're adding the last two numbers together, right? To make the next number. So 2 and 3 to 5, and the next will be 8, right? Because 3 and 5 make 8. So in order to write it recursively, what you might think is, okay, if it's less than or equal to 1, like if we want to find the nth Fibonacci number, right? Then what we would do, right, is we would say, okay, like, so here, this is the first Fibonacci number, right? This is the 0th one. So for the 0th Fibonacci number, we return 1, right? Or I guess this would return 1. But anyway, I guess it would kind of work the same. It would just be indexed from 1 instead of 0. But okay, we could do, let's just say it's indexed from 1. So just for simplicity's sake, let's say it's return 1. But it would still work together. So if n less than or equal to 1, right, we're going to return 1. So if it's this case or this case, we're going to return 1. But otherwise, we want to return Fibonacci number of n minus 1 plus Fibonacci number of n minus 2. So because that's exactly what we're doing, right? To find the nth Fibonacci number, like let's say we want to find the 4th Fibonacci number, right? The 4th Fibonacci number is 5 because 0, 1, 2, 3, 4, right? So let's label them 2, 3, and 4. So to find the 4th Fibonacci number, right? And we actually see here, but what we have to do, right, is we have to, for the 4th Fibonacci number, right, we know the 4th Fibonacci number is the sum of the 3rd one and the 2nd one. So what this is going to solve for us is going to say, okay, it's the 3rd Fibonacci number plus the 2nd Fibonacci number. And then we have to solve this for the 3rd Fibonacci number. So the 3rd Fibonacci number, we then solve it recursively, right? So it's the 2nd plus the 1st. And the 1st is a base case, so that one we're done with. But the 2nd is the 1st plus 0 plus 1st, right? And we're going to do the same thing with the 2. So if we can draw that kind of out as a tree. So let's do that. Let's do that. And actually we see it already drawn for us, but let's talk about that, I guess, instead. So that would work, right? And well, first of all, let's just clear up the fact that this is going to work, right? Because we're just solving subproblem. So we're solving for, here we're going to solve for the 2nd Fibonacci number. Then using that plus the 1st one is going to give us the 3rd. And that's going to be correct, right? Because the 3rd is the 2nd plus the 1st. And then now that we've solved, and then we solve for the 2nd, right? So we solve for the 3rd, we solve for the 2nd. And then some of those is the 4th. So this is going to give us the correct answer. And that's completely fine. But there's kind of a problem here. And let's see what that is. So let's erase this really quickly. And the problem for us is that we're kind of like doing a lot of stuff again and again. So what we notice here is we're solving for f of 4, we solve for f of 3 and f of 2. So far, so good. But notice we're solving for f of 2 again, and we have to break it up into 2 subproblems again. And the same thing over here, like we're doing this step like 2 times. So this tree happens twice, right? And if it's a bigger tree, like let's say we have f of 5, right? We're going to see then f of 3 in both the left and right subtrees, right? Because on the left, or on the left subtree, right, we're going to have just f of 3. And the right subtree, we're going to have f of 4, which is then going to make f of 3 and f of 2. So we're going to keep seeing the same things again and again. And that's not good because we keep solving the same problems we've already solved, which kind of defeats the whole purpose, right? And maybe an easier way to think about this, right? Yeah, and yeah, so we'll talk about the tree in a second, but maybe an easier way to think about how we could possibly solve this, right? Is what we notice here is like, here we have a base case, right? In our base case, we just have one single return statement where we're done. What if like there was a way to say, okay, well, like we solved for the second one, right, already. So like, that's kind of a base case, right? Because like a base case is something you already know the answer to, right? And like, you don't need to go back and compute it again. Like essentially, that's not the reason why we have a base case. We have a base case, we have a terminating step. But you can also think of a base case as like, for example, if every case is getting it down to f of one, and I know the answer for f of one, then I can just set it as a base case. I wouldn't need like f of negative one or whatever, right? So maybe there's a way for me to set like 2 as a base case, so I don't have to get all the way down to 1 once I've solved for it. That's kind of the idea of dynamic programming, but we'll talk more about that in a second. But let's talk more first about what the problem is, right? So generally, the problem, as we mentioned, is we're solving the same problems again and again. And why is that bad? Well, this tree here, right? Basically, this for every element in this tree, we have to do some sort of computation or calculation. And how tall is this tree? How big is this tree, right? Well, the height of the tree, right? Notice that the tree is going to be approximately a level, right? Because the left side and the right side, like in the worst case, right, we can think of it being like all of the nodes at the same level. And in this case, what's going to happen is that how tall is the tree going to be? Well, if we go just look at the right children, right? For the right children, we only go down at 1 each time, right? So 4, 3, 2, 1. So that's a problem because the height of the tree is 2 to the n minus 1. Or the height of the tree is n minus 1, right? Is what I meant. But then the number of nodes in the tree is bounded by 2 to the n minus 1. But we're going to have something kind of close to it. Now, it's not exactly that because, as you may notice, right, we don't, on the left tree, we go down by 2 each time. So it's not quite as bad as 2 to the n minus 1, but it's pretty close to it, right? And what it actually is it's closer to, as we see here, 1.6 to the n, which is still really bad, right? That's exponential. And that grows exponentially. That's not good. So you can look more at the analyses if you want to. But yeah, and 1.6 is to the n. That's a lot of things we're doing a lot of times. But if we think about this problem, right, if we think of the Fibonacci problem, right, it's like, okay, if we have the fourth Fibonacci number, that's the third and the second, right? And then the third and the second, that's the second and the first. But notice the second here, if we solve for it here, we can just say, okay, we've already solved for it. Why solve for it again? Because we'd have to go make a subtree again. But if we've already solved for it once, why not just say, oh, I already know the value from here, just replace it. And that's the idea of dynamic programming, is that there's some sort of overlapping subproblem, as we call it, right? There's subproblems that happen again and again, right? Or like the subproblems overlap. So here we have f of 2, we solve for multiple times. So there's an overlap, right? Because the subproblem for f of 3 overlaps with the subproblem of f of 2, because both of them have to solve for f of 2. So if we can just solve for one of it, if we can just solve for f of 2 one time, then we can just like use that value. So that's one of the main characteristics of dynamic programming, overlapping subproblems, because the subproblems, if they overlap, right, you solve for it once, and you don't solve for it again. You just store the value somewhere. And then optimal substructure. Optimal substructure is where there's some sort of structure to the problem where the optimality like of it in like in a local sense, right? So like here in f of 3, right? This is optimal. Like this little tree here, if you solve for the f of 2 here, like that's still the optimal way to solve for it, right? That's the optimal solution for f of 2 you can solve for here, which is still the same as the optimal solution for f of 2 here. So like there's some sort of substructure which is best, right? And if we get that best thing in the subproblem, in the substructure, right, then maybe we can use it again with the overlapping subproblem. So I know this may have been a little bit confusing, but that's kind of like a general overview of dynamic programming. Okay, so maybe now that we kind of have some sense of it, we can see how it applies in the Fibonacci example. Okay, so hopefully you're with me so far. I know that's a lot. Okay. But let's do a poll question first. So which of the following statements are true as to why Fibonacci example might call for dynamic programming approach? All right, so you can pause and try and answer. And so the answer is, it's all of the above, right? And it's all of the above because it's, first of all, it has an exponential runtime, which makes it impractical, right? Because the whole tree, right, is 2 to the O of 2 to the n, or O 1.6 to the n, as we saw. And that's kind of impractical. It has overlapping subproblems because we solve the same subproblem multiple times. Like f of 2, we solved multiple times when we were solving for f of 4. And so it's, yeah, the Fibonacci recursive problem, it's impractical and inefficient because you keep repeating the same problem. But dynamic programming, the whole idea of dynamic programming is you're solving subproblems and storing the results. So it gives us a better runtime because you don't have to compute it again. So let's look back at this tree here for a second and see what it would look like with dynamic programming. So if we're solving for f of 4, we solve for f of 2, and then somewhere we say, okay, f of 2, right, is equal to, well, we happen to know, right, that that's just going to be 2 because we're going to solve f of 0 and f of 1 here, right? So far we've stored f of 2. And we solve for f of 3. How do we solve f of 3? Well, f of 1, we already have, like it's return n, so we're going to return 1. That's not a problem because a base case, we don't go any further anyway. But f of 2, rather than solving for it again, we say, okay, let's use the value we already stored. We already stored it here, which means we don't have to even look at these. We don't have to go any further in the tree. This just becomes f2. We just replace this with 2. So what we notice is that we don't ever make any more recursive calls. Once we get down to 2, we don't have to go further. And then now that we've solved for 3, if we ever have to solve 3 again, we don't have to do that. We just have it stored already, right? We have it stored in memory as 3, right? So the idea here is that we only, like, other than, like, every single one of these, right, f of 0, we only have to get down to 1 time. F of 1, we only have to get down to 1 time, or I guess 2 times because one's in each subtree. But after that, we never have to reach the base cases again because we don't have to do the summations because we have f of 2 stored. So next time we see f of 2, we're just going to replace it with the value we already know. Next time we see f of 3, we're going to replace the value we already know. Something like f of 4, right? So as you can imagine, as the tree gets bigger, there are more and more subproblems that overlap, and we can just replace them with values that we're storing, which makes it a lot faster because we don't have to go down the tree to compute things. We already have them saved somewhere, so it makes it a lot faster. That's the, like, kind of how dynamic programming works. That's how it works for this problem. So let's look at the example a little bit more. So again, I know it's kind of a lot, but dynamic programming I know can be kind of intimidating at first, but it's really just a useful tool to solve these kinds of problems. So let's look at a memorization example, or memorization table. So this is just a table that keeps track of it. So this is where we're storing it, is in this table here, right? So let's look at it. So we have f of 4. We're trying to solve for f of 4. So we have to solve for f of 2. F of 2, we have to use f of 0 and f of 1 to solve for. So we already know the values of those. We know the values of those. Again, I was using 1 indexing before, or 0 indexing for the Fibonacci sequence. This is using 0 indexing. So it's going to be, or it's going to be using 1 indexing. So it's going to be a little bit different because it's using its first Fibonacci as the first index. I was using it as the 0th index. It'll still work. It's just a little bit different. So just to be clear. But okay, the table looks like this. It's like, oh, these are base cases. So f of 0 is 0, f of 1 is 1. And then f of 2, now we solve for is 1, right? And we solve for it as 1 because it's just the sum of those two. Okay, now we have it stored. Now we're going to solve for f of 4. F of 4, like, in order to solve for f of 4, we solve the left one. Now we have to solve the right one. So solve for f of 3. Now f of 3 is just 2. And the way we know it's 2, right, is because we know that it's f of 2 plus f of 1. But f of 2 we just grabbed from our table rather than having to break it into a tree even further. So that's the great thing about dynamic programming. It made something that was 1.6 to the power of n, or 2 to the n, right? It may go up to just O n. And it's only ON because what you may notice here is that really we're just solving for each integer from like 0 up to the nth Fibonacci number one time. We only have to solve 0 one time, 1 one time, 2 one time, because after that they're in our table. So we don't have to solve for them again. We just grab the value that's already there. So that's what makes dynamic programming great. It's like you don't have to solve for things again. So it makes it a lot faster. That's the idea here. Okay. So for the code itself, how will we do that? Well, we create an array to store the previously computed values. So our starting conditions are index 0, we make Fibonacci 0, index 1, we make Fibonacci 1. And then if n exists in our array already, right, let's say we've already found, that would mean that we've already found it, right? Then we just return table n. Otherwise, the nth element of the table is going to be the n minus 1 Fibonacci number plus n minus 2 Fibonacci number. And we do that recursively, right? So now, let's say we haven't solved for this yet. Well, we're going to do that recursively. We're going to solve for Fibonacci n minus 1, and then the same thing for Fibonacci n minus 2. And then at the end, we're going to return table 1. And that's it. So that's how the code works. So again, I know dynamic programming can be intimidating, but it's not so bad. I promise you, like once you understand it, it's pretty good. So what is it exactly? It's a method of solving problems similar to recursion, and it usually or very often uses recursion. The only difference is that the information you're working with, you dynamically update as the function runs. So you're sometimes like storing values, for example, and that's often a big part. So you solve problems that are solved by smaller subproblems. So there are smaller subproblems, and let's say you're solving the same problems again and again, then well, you would use those solutions. So often they're used for optimization problems, so bin packing, for example. And the idea is that solutions to subproblems are saved. So you don't have to calculate them again. You could just use the thing you saved, which is a lot faster than calculating it, right? Like accessing something from an array is like really fast, right? It's instantaneous. But if you have to compute it, like it may take a very long time because you may have to compute something very large. So often you store things in a table or an array, and it's called memorization. And this is constructing a bottom-up approach. And we'll talk about top-down as well, which is the opposite, but they're both dynamic programming. And brute force solutions, like the one to Fibonacci that we just saw that was recursive, are a lot more computationally expensive because you have to calculate the same problem multiple times. And dynamic programming solves this, right? Because it stores the subproblems in a table and then just looks them up rather than solving them again. And that reduces the number of recursive calls. So a lot of times when you're writing a dynamic programming solution, you start with just a brute force solution. But then instead of just like always using the brute force method, it's like you only use brute force if you don't have it already stored. Then you just replace it. You're like, oh, if I've already stored it here, like in my array, then just use the stored value rather than computing it again. So a lot of times you start with brute force and then just use your stored values instead. That's one very common way to see dynamic programming used. Okay. So required properties of the problem. So overlapping subproblem, right? And overlapping subproblem is you see the same problem, you've seen it many times. It's just like here, we saw f of 2, we did ones, f of 1, f of 0, f of 2, f1, f. And we're doing the same thing again and again. That's not what we want to do. So for optimal sub, and then that's the overlapping subproblem part of it. Optimal substructure is, yeah, it's like divide and conquer, in that, yeah, the optimal solution to a problem you get to by like you combine optimal solutions of subproblems. So it's not quite like greedy, but and it's not quite like divide and conquer, but like it's similar in a lot of ways because parts of the problem that are optimal locally might, like instead of with greedy, where local solutions, remember we were talking about how local solutions, if it's optimal locally, it's going to be optimal globally, or working towards the global optimal. And that's not, the difference is that dynamic programming, the local optimal, we don't know if it's going to be part of the optimal solution, but there's the possibility that it is. And because there's a possibility of it, it's something we need to consider. So rather than like considering everything possible, we only consider, and this is kind of a common approach anyway, we often only consider what's optimally, locally optimal. So basically what you were doing is with optimal substructure is the optimal solution, yeah. You take a combination of local optimums. And then a lot of times, or actually wait, with dynamic programming, what you use a recurrence relation. And a recurrence relation is some sort of recursive definition for how we solve the problem. And this is, for example, is the Fibonacci recurrence relation. And this right here defines basically what our function was doing. We have our base cases, right? If it's n is 0, 0. If n is 1, 1. Otherwise, it's n minus 1, n minus 2. If n is greater than 1. Now, the difference in implementation is we actually have to store those values, like 2, right? But this is the recurrence relation. Okay, so hopefully that covers DP. All right, so whole question 2. So how does dynamic programming differ from divide and conquer? And how are they similar? Okay, we can try and answer it, and we can, you can pause if you want, we can go over it now. So let's start from the bottom. Let's start from D. They have no similarities. That's not true, right? There are similarities. So no, not quite. There's the exact same, and they're not the exact same, right? We've talked about how they're not the exact same because with divide and conquer, maybe you're solving, like maybe there's some, divide and conquer, the thing is the similarity, let's go to the similarity between them. And the similarity between them is that they both depend on optimal substructure, right? Because both of them, like if you think about, let's think about, I guess, binary search, for example, right? You have a sorted array. And in that sorted array, let's say we want to find 2, or let's say we want to find 1, right? The substructure is the same because we look in the middle, right? And if it's not there, then we search the left half. But in the left half, we're doing the same thing because the structure of the data is the same, right? And the way we approach it is the same. But they don't have overlapping subproblems. There's no overlapping subproblems because let's say you've solved the right half. Like that doesn't, like we know it's not in the right half. Like we've solved it in a sense. That doesn't tell us anything about the left half. So, and there's nothing similar, right? You don't have to store any values, right? You're not using the same solution again and again. Just because it's not in the right half doesn't mean that like 3 won't be in the right half, for example, or something like that. So there's a substructure that's the same, right? And that we know it's like entity. We do the same thing, whether it's in the left half or right half. We're just going to call it recursively, and so there's the same optimal substructure, but there aren't overlapping subproblems with divide and conquer, whereas there is with dynamic programming. So we're going to go with A. Or we're going to go with B. Sorry, we're going to go with B. B. They both depend on optimal substructure, but divide and conquer has non-overlapping subproblems. So our explanation for it is dynamic programming has subproblems be repeated, while divide and conquer does not. And yeah, that's why quick sort and merge sort, for example, work, is that they have some substructure that's optimal. And, that's not true with dynamic programming. That's not just what dynamic programming does, right? You can't just, or you don't just use the optimal substructure. You also use optimal subproblems by storing values, right? There's no reason to store values, merge sort and quick sort. There is with dynamic programming. Okay, so DP approaches. So there are 2 main ones, and they both are dynamic programming. One's bottom up, one's top down. Well, what does that mean? Well, okay, first of all, the bottom up approach is called tabulation, and top down is memorization. So memorization is a lot easier to code in general. Tabulation is a little harder to code, but tabulation is generally faster because you ahead of time you know the order and dimension of the table. Memorization is generally slower because you have to actually go ahead and create things on the fly. So like you have to. Sometimes there will be more things on the stack at a time, for example. Yeah, and for table completeness, in tabulation, you're always going to fill the table of values that are the subproblems, right? Like the subproblem, for example, f of 0 to f of 4. For tabulation, you're always filling the entire table. With memorization, that's not always the case. Sometimes you don't have to fill the entire table because maybe you don't need it all, right? Maybe there's a reason why once you find your solution, right, it didn't involve some values. Like maybe, for example, I was solving a problem with a different function and it doesn't happen to need f of 3. I don't need to fill f of 3, right? Whereas with tabulation, I'm going to fill it anyway. So let's see the tabulation approach for Fibonacci. Specifically, Fibonacci of n, we set table of 0 and table of 1 to 0 and 1 respectively. And then we go from to up to n and fill everything. That way, at each point in time, right, I can look back and I already know that the smaller subproblem, I already have it computed, right? I don't have to recompute it because I'm starting from the bottom. I'm starting from 0 and 1. Like anytime I'm calling something smaller, like n minus Fibonacci of n minus 1 or Fibonacci of n minus 2, I'm guaranteed it's already solved. So that's why it tends to be a little bit faster. Memoization, on the other hand, if it's less than or equal to 1, you return n. Otherwise, and I think memoization is a little easier to code, makes more sense. Otherwise, if you have memoization of n already stored, like let's say you have the value already stored, you just return it. If it's not already stored, you have to go solve for Fibonacci of n minus 1 plus Fibonacci of n minus 2. But remember, that still won't require us to make that many function calls, because as soon as we get down to something that is stored, we're going to use this else if statement. We're going to store it, right? And yeah, and I think, and then yeah, else memoization of n, right? If we don't already have it stored, the important thing here is that we're storing it here. Like if it wasn't already bound, like if we didn't already solve for it, we're going to solve for it here and we're going to store it in our table. So in the future, when we have to do a lookup, it'll already be there. So we don't ever have to, for any given n, we solve for it one time, but after that, it's going to be in our table. So we don't have to do it again. The next time we can just look it up. And then we just return the value. So that's dynamic programming. So let's look at another example. Or first, let's do a poll question. So which of the following statements are true about memoization? Top down and bottom up, or memoization and implementation. So pick all that apply. And you can pause if you want to try and answer it. Okay, so let's try and solve this or figure it out, right? So tabulation stores values in a table in sequential order. Memoization does not necessarily fill values in sequential order. So, okay, so storing values in sequential order. But is this true? Well, let's look back at our example. And in our example, we actually do see exactly that, right? We have to go into sequential order, tabulation, whereas for memoization, there's not necessarily any answer to it like that. So this is true. And memoization is better when not all subproblems in the subproblem space need to be solved. Is this true? Yes, it is, right? Like we said before, right? The table does not have to be fully computed, whereas with tabulation, it does. So if we don't have to solve for all the subproblems, then memoization is going to be better because we don't need to solve for all the things. So we're putting extra information for tabulation. We don't need to. So 1 and 2 are both true. And the next one, tabulation works better when not all subproblems need to be solved. Well, that's not true, right? Because it's going to solve for all of the subproblems, whether we need them or not, in tabulation. So that's not necessarily true. And it's in general not true. And for the next one, memoization is always better than tabulation. That's not true at all. And the reason why it's not true, right, is that, for example, if we have to solve for all the subproblems, then generally tabulation is better because it's going to solve for things a little bit faster. And it's faster, not in terms of big O notation. In big O notation, they're always pretty much always the same. I can't think of any examples where it wouldn't be the same, but tabulation tends to be a little faster, as you see here, because you already know the dimensions of the table. And memoization, you actually have to like fill the table backward or back up. So we have to put recursive calls in the stack. And here, like what we see on the left for tabulation, is we're not having to make recursive calls really, but memoization we do. It's going to take a little longer. So 1 and 2 are true and 3 and 4 are false. Yep, and yeah, Fibonacci solution appears to fill it in a sequential order, but for other problems, it might not. And actually looking back, if we did n minus 2 here, Fibonacci of n minus 2 and n minus 1, it actually wouldn't even fill in a sequential order because it would go down 2 at a time and then it'd fill in like the gaps as well. Like it would, if we were solving for f4, it would first solve for f2 before solving for f3. So, and that would still be valid memoization. Even though in that example, it looks like memoized fills in a sequential manner, it doesn't. Okay, so let's talk about implementing DP. Okay, so hopefully you're with me so far. I know it was a lot, but hopefully you have a good idea of dynamic programming now. So now we're going to go over an example. So now let's do a different example. So if we're given two strings, find the edit distance. Edit distance is the number of edits to get from one to another. An edit can mean insertion, deletion, or replacement. So if we're given the input race car, we want to output racetrack. So what would be the changes? How many changes? And what would the changes be? Well, we know we can figure this out on our own, right? Like just sitting down looking at them. And the output would be 4, right? Because there are 4 changes. And to get from race car to racetrack, these are the changes you can make. Now I'm going to give you a minute to kind of try and think of, okay, how can we do this? If you want. And then, well, once you're done with that, if you want a second to think about it, you can pause and think about that. Then we're going to go over kind of an approach. And if you want a hint, I guess, would be a good place to start is often with the recurrence relation, which we talked about earlier. Is like the definition for the solution. And a way to think about the recurrence relation is using the fact that these are your 3 options. So just to think about that, right? Okay. And sometimes, like for example, you may not want to change anything. So, okay. Now we're going to start going over the solution for it and going over the example a little more in detail. Okay. So bottom-up approach. So we notice that they're overlapping subproblems, right? Which is why dynamic programming is perfect for this. And as an example, RACEC and RACIT have an edit distance of 1, right? And that helps us find the solution to the edit distance for, well, I don't even know how to pronounce these, but yeah, because they're not real words. And so the edit distance, if we know the edit distance to get to RACEC, then getting to RACECA is only 1 more. And getting to RACT is also only 1 more because we make 1 change. And yeah, the same problem solution is needed multiple times. We notice that because now getting to RACEC and RACETR, yeah, the edit distance 1 helps us to find the solution to edit distance for these, right? So we're solving the same problem again because we notice that some of these things appear more than once. So like we notice that we get to this multiple times, right? We also get to this, well, we get to this from here, we notice this appears multiple times. So we're noticing an overlapping subproblem because we're solving the same problem more than once, right? So, okay, so we notice the optimal overlapping subproblems, not hints that maybe the DP is necessary. How about optimal substructure? Well, okay, how can we use the knowledge that racetrack and racetraw have an edit distance of 3 to find the distance between these? Well, what you may notice, right, is that, well, the fact that these have an edit distance of 3, now what's the edit distance from here to here? Well, 1, right? And so if the edit distance to get to there is 3, and the edit distance to get from there to there is 1, then at the most, there might be a better way to do it, but at the most, the edit distance to get from here to here is 3 plus 1, which is 4. So that tells us that there's overlapping subproblems and optimal substructure. So we can actually come this recurrence relation, which is that for each, so we can look at I and J as the indices that we're at each word. So we have to go through the whole thing. But at index I, and then J minus 1, so we're looking at the previous thing on the other word. So we're looking for the minimum of these, right? And it's the distance from our word up to this point and the other word up to the previous point plus 1. So this would be like adding something, right? Inserting. And that would be 1 change. So it would be the number of changes. Basically, this is saying, okay, it's the minimum of these. It's the minimum of making an insertion, right? Well, if we made an insertion, right, then the number of changes we're making would be like 1 plus whatever the, or it could be a replacement, but, or deletion or whatever. But it's because we're making 1 change, right? So it's 1 plus however many changes it took for us to get to here, which was the previous, like the spot we're at in our current word and the spot one before, like how many changes they get to one before, and then we have to make one more change. So it's how many changes we have to get to before, and then one for the next edit. But if we're editing our, and this is if we're editing like the other word, right? We're adding something to the other word or replacing something or deleting something in the other word to make them the same so far. Whereas here, to make them the same so far, we're making a change to our current word, right? And then notice that it's 1 plus, because again, we're doing 1 plus however many changes it took already. But the other possibility is, what if at the current letters for each this word and the other word, they're the same? Like, then, okay, it's just how many changes we have to make in order for us to get the same word. Like if we're at letter I in this word and letter J in the other one, let's say that they're the same up to I and J. Now let's say I and J are the same. And how many changes do we have? Well, let's say that they're the same at I and J. Let's say we had to make some number of changes to make them the same up to I and up to J. Well, if they're the same up to those, right? However many changes we had to make to those is, let's say we call it K. We're just going to say K is equal to this value, di minus 1, j minus 1. Now that's the number of changes we already had to make. But if they're the same at this point, like the letters are exactly the same, we don't have to make an additional change, right? There's no reason to, because what we're going towards and what we currently have are the same. We don't have to make a change. So we're going to be adding, like they're the same, right? So we're adding them to the word, but it's this K, right? And we don't have to make an additional change. That's it. Okay, so it's changing this is like changing the second word, changing the first word, or keeping the same. So let's look at how we would actually draw that in the table. So let's start just filling the table. This is the number of changes it would take to get, or number of changes from these values. Okay. Notice that we're going to be using this, right? This recurrence relation. So from 0, and we're going to put 0 here because at the previous spot, right, there are no, like they're the same up to here, right? They're the same up to here, so we had a 0 there, right? There were no changes that had to be made. Plus, like the difference that we have to make in order to actually get to these letters, right? So R and R are the same, so no changes had to be made. So 0. But now we keep filling the table, and we're going to fill the table just using this recurrence relation. Now that we have it defined, we're going to go through the rest of the table just using this until we have to get somewhere. We're going to use something else, right? Besides just this bottom one. Okay. Now we notice we have to make a change because up to here, it's been pretty straightforward. And you notice 0 is along the diagonal here because that's kind of where we have so far. And that's because race here and race here are the same. So no more change will be made. But here we actually get a difference. So what do we have to do? We have to put a 1 here. The reason we're putting a 1 is because at index here, at like how many changes would it have to make in order to get this C into the T? Well, it would be 1, right? Because we're changing the C into a T. And so we have to put 1 there because it's 1 change. And up to there with 0 changes. Okay. So that's that. And that's why we have a 1. So far, the number of, basically what this means is that the number of edits to get race C and race T to the same is 1, which makes sense. It's 1 replacement. Okay. Now we fill the rest of the table in that manner. So the next time we notice, oh, A needs to change into an R, but also here, we can also go right and down. So if we're just going along diagonal, that's just a replacement. But we can also notice what happens as we move across because they're different lengths. So at some point we'll have to make other changes. So here, to make a replacement to get to A, this is one of the optimal ways to get there. So we're just going to worry about this way, but there are other paths as well. But in this path, right, we go 0, 1. We notice this 2 here. And this 2 is because we had to change the A into an R. And here we change the R into an A. And so that would mean we'd have 3 to get to this point. So adding 2 more would give us 5. But there's a better way to get there, right? So one possible way to get there is change race car by changing the CA and R into TR and A and then adding CK. That's 5 changes. There's a better way to do it. The better way to do it is this. So what we're going to have is still this 1. There's 1 change. But then at the R, right, what we can choose to do is instead like insert an R, right? We insert an R instead of what we were doing before, which was we were changing the A into an R. We want to use the A later. So, or the C into an R. Why not just like replace the R? So that's exactly what we do here, is we insert the R inside. And then the next thing for both of them is A. So we don't have to make a change. We just, the A stays the same for both. So no changes. And then now we can replace the C with an, or the A with a C. And then finally, we replace the R with a K. Or sorry, we replace the, my bad. We replace the R with a C, and then we add a K to the end. So those are our changes. So there was another way to go, which took us 5. There's a shorter way, right? And so that's what we just. So in order to get, if this gives us the number, but if you want to actually go back and get the optimal one, you can just trace back through this matrix or array. Whoops. And you can do that like this. We have a 4 at the end. So you go back where you saw it decrease by 1. You saw it decrease by 1 along diagonal. Then you go left and decrease by 0, decrease by 1. So wherever it decreased by the minimum is how you go back, right? Left to right or diagonally. Okay, so that's kind of complicated, but I hope that makes sense. So let's analyze this problem. So space complexity is just n times m. And the reason why it's n times m is because those are the size of the two strings, or it's n and m are the size of the two strings. And the reason why it's n times m is because, well, this is space complexity, right? And clearly that's the amount of space we had to use was like n rows and m columns. And the runtime is also O of nm because we just filled the array to solve our problem. And because of how we define our recurrence relation, each of these only takes over 1 time, each calculation, because these values, dij, d minus 1j, dij minus 1, and such, they all use pre-computed values. So you only have to compute each of them 1 time. So, and after that, you just use the stored value. The stored value, using something that's stored just takes over 1 time, right? So it's O of n times m time, but also O of n times m space. Okay, I know that was like a lot, so it's okay if you have questions, like you can of course message me on Slack, for example, and hopefully this kind of makes sense and give you an overview of like what dynamic programming is and how we'd use it, why we'd use it. Okay. So complexity theory. So complexity theory, so this is, yeah, as I mentioned before, this topic I really like to go over, so this will be interesting. Okay. But it's a little bit, maybe not something you'll be using every day, but it's something it's definitely good to know about and to kind of have an idea of what it is. So there are a couple different classes of problems we can classify problems into. And for the most part, the only ones you're going to have to really worry about are these, right? Like there's the classes P, NP, NP hard, NP complete. There are more. So like there are recursive, and then they're like RE, so like recursively enumerable, or yeah. And so like there are a lot more classes of language, like many. And these are just like a small subset of them, but they're the ones that we interact with most. So they're the ones that we're really concerned about here. Those are the only ones really that we actually go over in this class. But there are other classes you can take at UF where you learn a little more. Like I think data computation has a class you can go over more, if this is interesting. But anyway, there's P, NP, and NP complete are the 3 classes of problems that we're going to discuss. And P problems, these are any problem that's polynomial can be solved in polynomials, right? So P, the class of P is, this is a set of all problems that can be solved in polynomial time. And polynomial time just means that there is some algorithm to solve the problem that doesn't require exponential time, right? Like it's, for example, O of 1, O of n squared, O of n cubed, O of log n, like all of those, anything that's not exponential is in the class of P. NP stands for non-deterministic polynomial time. And NP problems are ones that can be verified in polynomial time. Well, that may sound weird, but what it basically means is it's a set of all problems that if I give you a solution to the problem, right? If like, let's say you're looking for a solution. If I give you, okay, I'm like, okay, well, maybe you could solve it, maybe you couldn't, I don't know. If I give you a solution, you can write an algorithm to check that that algorithm does indeed solve the problem in polynomial time. So like, I don't know, if I gave you some sort of traversal, right? If I give you the output of the traversal, you can definitely check, right, in polynomial time and make sure that, yeah, it's a valid traversal, right? Or you can like trace back there. If I give you the nodes, you can be like, yeah, okay, you went along the nodes, like that's valid. So a verification in polynomial time is a set of NP, so non-deterministic polynomial. NP hard are all the set of problems that are at least as hard as the hardest NP problems. So what this means is if one solution, okay, so yeah, NP hard includes the set of NP complete, we'll talk about in a second, NP. And the thing about NP hard is that NP hard could include more things. And in fact, it does, or NP in general does. So NP hard problems, basically any problem that's NP hard, right? Because it's at least as hard as the other NP problems, if you can come up with a solution for any NP hard problem that runs in polynomial time, then you can use that as like almost like an oracle, right? Like you can pass in, or you can modify it slightly. So then you can just like pass in anything else that's in NP, because everything else in NP is no harder than it. So you can use any other problem that you can't solve. You can use this one solution to this problem for all the other problems, because you can modify the other problems so they fit this problem's input in polynomial time, and then solve this one in polynomial time because it's NP hard. So, and then all of the things in NP hard then just become P, right? It all collapses down to P, because anything that you solve in polynomial time, or in anything in NP hard, right? If you could solve one thing in NP hard in polynomial time, well, everything else in NP hard is just as hard as it. So, or just as easy, or is just as easy as it. So then those must also be P. But that's, I know, a little bit of detail, but basically NP hard problems are at least as hard as NP problems. And so if there's a solution to one NP hard problem, right, the rest can all be modified using a polynomial time reduction. So polynomial time reduction just means like you can modify the input of another problem to fit the input of this problem. So then NP complete problems are problems which are both NP and NP hard. So basically, NP complete problems are both an NP and NP hard. But NP complete problems, NP complete problems are not in P, because P problems, right, can be solved in polynomial time. NP complete problems are NP hard. And if it's NP hard, then it's at least as hard as the hardest NP problem. But it's not, and it is NP. So all P problems, right, are not necessarily as hard as all other NP problems, right? So that's why NP complete problems are not the same as P, because P problems are easier than a lot of other NP hard problems, because NP hard problems include problems that we solve exponential time only that we know so far, whereas P problems can be solved in polynomial. Okay, so hopefully that makes sense. And yeah, sometimes they're used interchangeably, where NP complete and NP hard, but really they shouldn't be, because they are different. As we can see here, like there's definitely a difference between them. So, although I mean, actually, yeah, like they're similar, right? Yeah. So often, or NP complete problems are both an NP and NP hard. So sometimes they're used interchangeably. Okay. So, yeah, because like for our purposes, especially, they're basically the same. And yeah, if you want more depth on this, it's here, and a reduction is here. So yeah, those polynomial reductions are kind of interesting to work through. So, well, why do we care? Well, first of all, it's good to know, because if you have to solve a problem that's NP hard, right, then you can't solve something that's NP hard in polynomial time necessarily, that we know of, right? So if your boss like goes and tells you, oh, you have to solve this problem in polynomial time, it's good to know that you can't do it, for example. And it's also a famous problem in mathematics, in computer science mathematics. And yeah, Karp's 21 problems are problems which are NP complete. And yeah, anything inside you can easily reduce. So in fact, vertex cover and complete problem are very, very similar, except acting like, yeah, the reductions like that. And actually, knapsack. So knapsack problem, for any of you have heard about this before, is actually NP complete. And interestingly, right, if you've heard of knapsack, you may think, oh, that's a DP problem, and you can solve knapsack with dynamic programming. So you might think, okay, but isn't that not NP complete? Like, I can solve it in polynomial time. Well, it's only polynomial with respect to the number of elements of, it's only, sorry, not with respect, not the number of, it's not polynomial with respect to the number of inputs. It's polynomial with respect to like the size of the input, but not, or like the size of the optimal solution, right? It's polynomial with respect to the size of the optimal solution, but that size of the optimal solution, right, doesn't really have to do with like the number of elements in your input, or it has to do with like the number of elements in input. So it's not polynomial with respect to the number of bits, because the number of bits that it gives out is 2, so like 2 to the power of the number, right, is the number of bits, right? Or sorry, it's the number of bits, right, is going to be much larger than the actual number, or is much smaller than the number itself. So it's polynomial. It's not polynomial, even though it may seem like it is. So we can solve knapsack using DP, but it's still not actually a polynomial time. So just, and okay. So what about the SAT problem? So Boolean satisfiability problem is one that looks like this. It's the problem which checks with whether a given Boolean formula has a combination of true and false to its variables that make the output true. And if that's the case, it's said to be satisfiable. This is like, the father of all, NP complete problems, because it was the first one to be proven to be NP complete. So now if you ever want to prove that something's NP complete, you only have to do a reduction from this problem, the SAT problem, to your problem. So if you can change this problem slightly to be an input to your problem, right? And you're just like, oh, but you can change it in polynomial time, and then your solution gives an output in polynomial time, or your output is supposed to give an output in polynomial time. You can say, oh, that's not possible unless NP and P are the same, because otherwise we'd solve this problem. And this problem is NP complete. So yeah, and no known algorithm that efficiently solves it. The best we have are exponential time. So generally I believe that there isn't an algorithm which can solve it, but we haven't proved that mathematically, and it'd be quite difficult to do. And many people have spent a very long time on that. Yeah. So basically, the question boils down to, are P and NP the same, where P is the set of all problems which are can be solved in polynomial time, and NP is a set of all problems which can be verified in polynomial. A solution can be verified in polynomial time. And general consensus is no. There's been no proof for it yet, and it's a really big problem in mathematics and computer science, for that matter. And a solution for it, yeah, would yield $1 million reward. But it's a very, no one has ever shown it because it's a hard problem. And yeah, it's widely believed that P not equal to NP. It'd be very surprising if that were not the case. So yeah, but yeah, that's an open problem. Okay, so fun facts. So P is not equal to NP is one of some millennium problems, and that's why there's $1 million reward for it. The first person to provide a correct solution. I think only one of the 7 millennial problems has been solved so far, if I remember correctly. But this is definitely not one of them. And P is equal to NP is significant in computer science for sure, because it's, and mathematics and cryptography and artificial intelligence, it's very, very relevant, because a lot of systems we use now rely on the fact that P is not equal to NP. So we often use algorithms or rely upon the fact that there are not algorithms to solve something quickly. And so it would break a lot of the, for example, cryptography we have now. And yeah, it would be a lot, for example, it would be a lot faster to break the encryptions if there were a polynomial time solution, right? Because polynomial times turn faster than exponential. So that would make things a lot faster. But fortunately, it does not seem that they are equal, but there's no proof for it, right? So this is kind of the assumption that we operate under, something like this. Although this is also a possible. And NP hard problems are at least as hard as NP problems. NP hard problems do not have solutions verified in a long time. Yeah. Yeah, so there you go. But, or not necessarily anyway, right? NP hard problems do not necessarily have solutions for polynomial time because NP complete problems like exist within it. NP is inside of NP. Yeah, possibly, right? Like NP complete is inside of NP hard, right? But not all of NP is necessarily. So that's exactly why earlier, even though we mentioned that generally NP complete and NP hard are kind of the same, they're not, because like even though we sometimes use them interchangeably, they're not the same. Because NP hard, regardless of whether P equals NP, may still include like things outside of P and NP complete, because they're all even harder problems. It includes things which are harder than even NP. So I know that's a lot, but yeah, it's kind of some interesting stuff. So hopefully you got something out of it. And okay, I guess there's a little more. So let's go through that. So TSP problem, for example, is one which is NP complete, and it's a problem which, given a list of cities and distances between each pair of cities, what is the shortest possible route that visits each city exactly once it returns to the origin city? So this is the Hamiltonian path. It's closely related to the Hamiltonian path problem, in that you want to visit everything exactly once and return back to your starting point. And it's NP hard, right? Brute force is just O of n factorial. You can use dynamic programming, but it's still O n squared times 2n. It's better, but it's still exponential. And generally believe that there probably isn't. And if P equals NP, then there would be a polynomial time solution. But if not, which seems like there probably isn't a better way to do it than exponential. Because this problem actually can reduce and does reduce to the SAT problem we talked about earlier, which is why we know it's complete. So poll question number 4, which of the following are verified to be true? So select all of them. You can pause if you want. Overhead. So, all right. So the first one, P is equal to NP, absolutely not. In fact, the opposite is widely believed to be true, but it may not be, right? It may still be P. So yeah, this is not verified true. A problem can be both P and NP. Yeah, absolutely, right? Like NP, this just means that you can verify the solution for it. Like if I give you a solution, you can verify in polynomial time. So pretty much, yeah, like any problem which you can solve in polynomial time, you can then verify solution in polynomial time as well. So basically every problem in P is an NP. So any polynomial time, any polynomial problem that is polynomial or any problem in P is also in NP. So yeah, this just includes a set of all problems in P. So problem can be both in P and NP complete. So this is not the case unless P equals NP. So conditionally no. And this is because NP complete include all the NP hard problems, and P is not NP hard, unless like NP hard has no intersection, or NP hard, right, does not have an intersection with P unless P equals NP. Or sorry, P and NP complete, right, don't have an intersection unless P equals NP, because then everything in NP would also be NP. So unless P equals NP, this is not true. All NP hard problems are NP complete. Yeah, this is also not true. This is not true because remember, NP complete just includes problems which are both NP. So you can, if you're given a solution, right, you can verify it in polynomial time. Yeah, if you're given something as NP, you can verify it in polynomial time that it's a correct solution. But NP hard includes not only those, but it's at least as hard as everything in NP. So it includes everything in NP, but it's also could include a lot more. And it does. And all NP hard problems can be verified in polynomial time. Yeah, this is not true either, right? Because for the same reason as before, NP hard problems, not necessarily, or this is not true because NP hard problems, right, includes more than just NP. And NP can be verified in polynomial time, but NP hard doesn't just include NP. It includes things beyond NP. It's at least as hard as everything in NP. So it includes everything in NP and then further. So really the only one that we can verify true is the second one. See, yeah, so, as you said, right? You can kind of use this diagram as a way to know this. Like the only things that have been verified are basically the stuff on the, well, like the only things that are verified are that like, yeah, is that P intersect with NP, it's just P. And then the rest of it, we don't know, right? Okay, so hopefully, yeah, so this is the graph of NP complete problem. And as you can see, it's very complicated. And of course, there are a lot more than this, because any problem that you can come up with, which you can reduce to, or sorry, any problem that you come up with that can be reduced from the stat problem, or any of these problems for that matter, like any of these problems that you can reduce to any problem in NP complete, which you can then reduce to your problem in polynomial time, is also going to be NP complete. So this is just like common. Basically, this is just a graph of common NP complete problems. As you can see, there are a lot of them, and the arrows kind of show what we reduced from and to. So that's just a visual. They can show you really the immensity of the field of complexity theory. It's some pretty cool stuff, but it's, of course, quite convoluted. And yeah, of course, yeah, there's a lot more to it. Like there are a lot more than just P and NP and hard and yeah, there are just so many different classes of problems and languages and all that. So, yeah. Question about anything else? Of course, you can message me. And yeah, as a reminder, you have a quiz. Choose next resources. Thanks for listening. I know it's a lot today. Hopefully you got something out of it. So thanks for listening. Have a nice day. Bye.